Hey, hello everyone. Uh, yeah, please welcome Victor. He is a professor at the Institute of Mathematics in University of Granada, and had the very nice opportunity of meeting him a few years ago. So yeah, take it away, Victor.
Okay, thank you, Praful. Well, thank you all the organizers for this great seminar on this very nice topic. Well, first I have to say that I'm not an expert in chemical reaction networks. My main topic of research is math optimization. So I will give you a brief introduction about why math optimization is useful and which are the tools that we use to analyze the problems. And then I will go to these connections that we found some years ago when I met Praful in medicine, and some of the things that we are doing now. So just to so optimization is nothing but the problem of when you have some decision to make and you have some kind of feasible solutions of some alternatives that you have to choose, and you have a measure about how good are the solutions, and then you want to choose kind of the best one. This is a general optimization problem. So in case all the things that are involved in this type of decision problems can be represented as mathematical objects, then we have a math optimization model. There are some people that prefer to say that instead of solving this problem kind of optimally, that they prefer to solve the problem heuristically and then trying to find a good enough solution. But in my case, I prefer to think about optimization problem as the problem of finding the best solution to a decision problem. Well, this field, which is math optimization, is a well-known field that's very practical, that's very useful in practice. And every day, many companies, many governments, many organizations are making decisions based on solving this type of problems, because you can represent your decision problem as a math optimization problem, then you can use the tool that we have to solve these problems and then make decision kind of efficiently. This is the case of logistic systems, when you have to decide which is the inventory system, or how to deliver some kind of goods to the final customer from the factory, or how to organize the machines to produce a kind of good, and everything integrated. Is a complex decision problem, but you use and you model the problem as a math optimization problem, you can make decision kind of efficiently. This is also the case of transportation problems, where you have to decide how to decide the times for the airplanes, for the flights, for different airlines, or for trucks, or for ships, or whatever. So where there are tons of parameters or decisions to make, and then you have to, if you are able to model that, there are many optimization models that are useful to solve this type of problems. Also for drone deliveries, that that now the Amazon is trying to incorporate drones to deliver some kind of goods, and they are doing some pilot experiences in Chicago and other places. Trying to know how to deliver in less than 3 hours an order. So optimization is useful there. Also, you use Google Maps then to compute the shortest path from one point to another. This optimization problem that we can model and we can solve very efficiently. Also, this is a typical problem, which is the salesman problem. This salesman that wants to visit a number of places and then come back to his home. And when you have tons of places to visit, this is a very difficult problem. And actually, it's an NP-hard problem. And but optimization tools can handle this type of problems. So this is the shape of a math optimization problem in general. So we represent our measure of how good is a solution as a function f, and we have a kind of constraints modeling which are my restrictions for the decision I want to make, and then I have a place and a space where the decisions are to be chosen, then this is a classical optimization problem. Probably you have seen this type of problems, and then there are many tools that about computing gradients, and then make them equal to 0, and then that's all. In general, that's not true, because in case the X space where the decisions are to be made, are to be chosen, it's not convex, or there are properties that are not verified, then this type of things about gradients equal to 0 is not valid. So there are other kind of approaches to solve these problems, and this is the case of network optimization. So what I have to say about this type of optimization problem is that math optimization is useful, but most of the problems that we have in math optimization are very difficult to solve. And some of the optimization problems that we want to solve, or those that most of the people want to solve, are those that arise in network design. So which is the problem that you have a graph, and you want to select or detect in a graph which are the interesting structures inside a graph, verifying some kind of optimality condition. And this is the case of chemical reaction networks. So chemical reaction network will give a brief definition about this type of thing, but in a chemical reaction network is nothing but a network in some kind of sense. And finding autocatalytic subnetworks is nothing but finding optimal substructures inside a chemical reaction network. So this is the math optimization for us is a kind of ideal framework to analyze this type of structures, right? So the problem we want to analyze with my kind of tool, this math optimization, is the construction, enumeration, or detection of autocatalytic subnetworks inside a chemical reaction network. So this problem is not to be NP hard. So it's not to be a very challenging problem. So it's not going to be easy now. So it's going to be a NP hard problem, but even if the problem is difficult, we want to provide solution of this type of problems, how to construct autocatalytic subnetworks. We use math optimization because for us, it's an ideal framework to do that. Because it has been proven to be very useful in other practical approaches. And also there are different steps that we need to apply to write or to analyze our chemical reaction network problem into a math optimization problem. The first one is to model the problem. I mean, I want to find a way to write my problem, my chemical reaction network problem, into a kind of math problem, optimization problem. And then the paper by Alex and his colleague is a perfect framework to find a way to model mathematically all the elements that are behind a chemical reaction network and autocatalytic subnetworks. And so I will model the problem first as a mathematical optimization problem, which is a very particular mathematical optimization problem, which is discrete. Discrete means that the decision to be made are chosen from discrete space, which is the case of most network design problem, because we will model the problem of selecting hyperarcs or hyper nodes of a network. So it's a yes or no decision about the choosing elements for a chemical reaction network. So it's a discrete mathematical optimization problem, so it will be difficult to solve, but we know that there are some math optimization, that some combinations of math optimization problem and autocatalytic problems. In this case, about detection or enumeration of autocatalytic networks, which has been where this combination have been very useful. That's in the paper by Seng some others, and the paper that we wrote with Raful, Eric, and David last year. So let me introduce the notation. So we have a chemical reaction network that we identify with a set of vertices, which are the species, a set of hyperedges, which are the reactions linking the species, and then the stoichiometry of the chemical reaction networks given by two matrices, S minus and S plus, which are the input and the output stoichiometry for each of combination of reaction and species, right? So which is, I think is quite standard. And then we use a kind of something that we introduced in our previous paper, but was also it was given also in the paper by Alex and others, and this is the definition of autocatalytic subnetwork, which is a substructure of a chemical reaction network underlying with a given set of species as a fundamental set, which is the set of autocatalytic species, which is the set M here. So for a subnetwork, which is a subset of species and hyperarcs, and a set M of a given chemical reaction network to be an autocatalytic subnetwork, the condition are the autonomy, which is that for each reaction there are species in the left and in the left and the right hand side of the reaction, and in the set of autocatalytic species, which is the set M. And that for each species in the autocatalytic set of species, there is a reaction in which the species is in the left-hand side and in the right-hand side, right? So this is the autonomy. That's something we call the species autonomy and the reaction autonomy of a subnetwork. And then the second condition is the productivity condition, in which to be autocatalytic, we need the existence of a flow, which is a combination of the reactions, such that the production of each of the species is positive, strictly positive. So each of the species in the autocatalytic set of species must be produced, positively produced. Right. So something that we found some years ago is that we can represent the problem, these conditions as a set of equations that can be incorporated into optimization problem. And the conditions are like, if we use the decision that we need to make, we have a chemical reaction network, and the decision is to select which are the species in the autocatalytic set of species, and which is the which are the reactions that we want to select from the whole chemical reaction network. Then maybe we can combine those elements, which are my decisions, and then by means of equations. This is so if I use a y variable to decide whether the species is in the autocatalytic set or not, if I use the c variable to decide whether the reaction is in the autocatalytic subnetwork or not, and x vector to decide which are the flows for this subnetwork, just combining them, we can model this type of condition. So the first condition, which are the species autonomy, is that for each species, these two equations must be verified, which is that if the y variable is 1, it means that the autocatalytic species is selected. Then the sum of the c variables must be greater or equal than 1, which means that there is at least one of the reactions in the set of reactions in the subnetwork, which is selected, where the this species is in the output, I mean, in the right-hand side of the reaction. And the other equation is the same, but for the input, for the reactants of the reaction. So we can write this condition about the autonomy just by writing a linear constraint using these variables. I don't know which are the values of the C and the Y. This is the goal of the math optimization problem, is to select which is the best combination of C and Y variables with some, I will let you know later, which is our goal to minimize or maximize. But so I mean, that's something which is usual in math optimization, which is try to find which is the best way to model logical conditions into linear equations or nonlinear equations. So this is species autonomy. For the reaction autonomy is the same, but so for each reaction, if the reaction is used in my subnetwork, so the value is 1 for the C variable, then the left-hand side, which is the sum of the y's, must be greater or equal than 1. It means that there is at least one species in the left-hand side or in the right-hand side of the reaction. And the productivity, which is that there is for each of the species in the autocatalytic set, the flow that we choose, there is, with each flow there is a positive production of these species, can be written in this way. So it's similar, but so in case the Y variable is 1, it means that the autocatalytic species is selected. Then the right-hand side, this part of the right-hand side with this delta, which is a big enough value, is 0. So it means that the left-hand side is greater or equal than epsilon, which is a small enough value. So which means that for this flow, the production of the ith species is greater or equal than something which is positive. So the production is strictly positive. So it's kind of how to combine everything to model these conditions. And then the final the equation is about that in case the reactions are not selected. So we model the flows as 0-1 continuous 0-1 variables, the flows and the set in only 0 or 1. So in case the C variable is 1, then the flow can be at most 1. But in case the reaction, the C is 0, it means that the flow is not possible to be greater than 0. So it's going to be 0. So it's like this stuff that we call the support condition. So the C is nothing but the way to select the flows that are not going to be 0 in the solution. So this is these are the only equation in my problem. And then if we incorporate them into a math optimization problem, and for instance, we minimize the sum. The sum is the number of reactions because we have 0, 1 values for the C variables. So if we minimize the sum of the C variable, then we are accounting for the number of reactions in the subnetwork. So if we incorporate all these conditions, this problem just give you the autocatalytic subnetwork with the minimum number of reactions. And okay, this problem is difficult to solve. I mean, it's a binary optimization problem because there are some conditions about the 0, 1 values that can be taken by the Y and the C variables. So it's going to be difficult, but anyway, we have a way to solve the problem in case, at least for medium-sized CRNs. And actually, there's another thing which is interesting in math optimization problem is that even if we don't want to solve the problem, this equation gives you the structure of the subnetwork. So if one can exploit, which is the region in this space of species and reactions, the region where this solution is feasible or not, or with this problem is feasible or not, or if there is any hope to find the solution more easily than solving this problem using optimization tools. So that's something that we were analyzing in our previous work. And with this type of model, we were able to enumerate the whole list of autocatalytic subnetworks for a given CRN. And then we started to think about if we have a list of something that was the minimal autocatalytic subnetworks, how can we measure how good in the set of all minimal autocatalytic subnetworks, that can be a lot, how to measure how good are those solutions among them. And then we were thinking about something which is the growth factor of a subnetwork, which is defined in this way. So if you are given a flow and you are given a subnetwork with a given set of, I couldn't say autocatalytic spaces, but with a subset of the species M that it will represent the autocatalytic species, but this way is general. So it's just for each of the species, I compute this ratio, which is the output production, it's the quotient in the output divided by the input product, and the consumption is the production divided by the consumption. And I compute that for each of the species in this set, M, and then I compute the minimum of that, if possible. And this is it's kind of a robust measure on how is the growth of the network for the whole set of species in the autocatalytic set. Okay, if I know which is the subnetwork and I know which is the special set M and I know the flow, I can compute this number just by applying the formula. But if we are given just the subnetwork, which is called the maximum growth factor, is nothing but the flow maximizing that amount, which is the flow that I need to use to find the growth factor as greater as possible, as larger as possible, right? This is a growth factor, which is something that was already introduced in other framework by von Neumman in the 40s. And then we thought about how to incorporate that into the problem of analyzing autocatalytic subnetworks. Then we first analyzed which is a relationship between the autonomy of a subnetwork and the value of this measure. And then if my subnetwork is autonomous in reactional species, then this value is finite. And also we know that the production of a subnetwork can be represented by means of values greater than 1 in the growth factor. And then what we know is that if we compute the maximum growth factor of a subnetwork and the subnetwork is autonomous, then the autocatalysis is translated into a value greater than 1 in the maximum growth factor. So, I mean, in general settings, autocatalysis is the same as finding maximum growth factor greater than 1. So, and that's something that we started to think. So first, how to compute these things, because we want to, the problem we need to solve is, which is the flow maximizing this growth factor. So if we are given a subnetwork. And because this problem is not easy, because these functions which are involved there are not convex, nor concave, are not linear. So the gradient equal to 0 is not a valid approach for solving the problem. So we need to use tools from something which is called generalized fractional programming. And this problem can be modeled in this different way, which is similar, but anyway. And then we analyze 3 different situations. We first provide an approach for computing just if we are given the subnetwork, how to compute the maximum growth factor using using an approach based on general fractional programming. The second situation that we analyze is what if the subnetwork is given, but we don't know which is the set M that the set that will represent the autocatalytic species is not known. So how to decide which are the best set of autocatalytic species taking part of the subnetwork? And this is the second approach. And the third approach is the one of how to compute, if we are given just the CRN, just the chemical reaction network, how to select the subnetwork such that the maximum growth factor is the maximum possible. So each of the problem is different but similar, and each of them. So the third one is generalizing the second, and the second is generalizing the one, and they allows different things. And the approaches are different by solving different optimization problems, right? So the ideas for solving the problem are not kind of sophisticated, but anyway, and the problem is different. That we use a iterative approach, and we know that converges to the optimal solution of the problem. Okay, I'm not going into detail of that. Then the first thing that came into our mind is so solving autocatalytic problems is a difficult NP-hard problem because we need to solve integer programming problem, which is a difficult type of problems. But how difficult is to compute the maximum growth factor? And then the first idea is, okay, let's try to find small CRNs and try to find which are the limitations of our approaches. And then we use this library SB Badgers to generate kind of realistic but random CRNs with the sizes in the size of the species of 10, 20, so on, to 50. For each of them, we generated 5 of them random. These are the pictures for the 10 CRNs. So the characteristics are different. Some of them are more dense than others. So a good representation of the network that we want to analyze. And then the first thing that we saw is that these are the box plots for the first approach, second approach, third approach. So recall that the first algorithm is just to compute the maximum growth factor. And then even for the 50 species CRNs, we found that in 15 seconds, at most 30 seconds, we were able to solve the problem. So that's okay. For the second approach, which is apart from the maximum growth factor, try to select which are the autocatalytic species which are better to maximize the maximum growth factor. And this is the second approach. And again, 25 seconds, 30 seconds, so similar times. And then for the third algorithm that also requires to find the subnetwork itself, we require in some cases 10,000 seconds, but in average like less than 1 hour in average for the 50 species CRNs, right? So this is I don't know if I want to say good news or not, but there is something which is good here, which is in case I want to, in the process of finding the maximum growth factor, I'm finding suboptimal solutions. That means that we can find subnetworks in which the growth factor is not the best one, but is going in the path towards one. And we represent here, which is the time to find for the first time a maximum growth factor greater than one, which means that the first time we find an autocatalytic subnetwork in our process. And in the first approach, which was easy, even for the whole process, but in this case, in 0.5 seconds, we find for the first time the first autocatalytic subnetwork. For the second approach, in less than 1 second, we find again the first autocatalytic subnetwork. So if we want to find one autocatalytic subnetwork, it's easy. And in the third algorithm that took a lot of time to compute the optimal solution, in less than 20 seconds, we were able to find the first autocatalytic subnetwork, which is a good, for us, it's what we need. Then we analyze, I think I'm out of time, but anyway, we analyze two real CRNs, the foremost CRN, which is a medium-sized CRN, and we found we ran the three approaches, and in a few seconds we found the solution, and we compare with the whole enumeration of the minimal autocatalytic subnetworks that we analyzed in a previous paper. And we observed that we were able to find we wanted to analyze in the minimal autocatalytic subnetwork, which was the distribution of this value, which is the maximum growth factor, and we were trying to analyze this amount for all the cores of the minimal subnetworks network, and also to analyze whether, because we were in the first approach that we analyzed 1 year ago, the goal was to enumerate the minimal autocatalytic subnetworks by means of the number of reactions involved in the subnet. In this case, the approach is different, but we wanted to analyze which is the relation between the number of reactions involved in that subnetwork and the maximum growth factor, and that's something that we analyze, and that at some point analyzing the number of reactions is related with the maximum growth factor. So the maximum growth factor is in general larger if the number of reactions is smaller, and the number of species is large, and in the other way around. So that's something that both approaches were kind of similar, but this approach is easy to solve. So I think that all the things in the conclusion I told you before. So that the math optimization is a flexible framework to analyze this type of things. That there is a lot of work to do to provide efficient algorithms for detecting and constructing autocatalytic subnetworks. And also there is something which is, we wanted to analyze some time ago with Praful and some people from Madison about how to incorporate mass action kinetics into the problem of finding the flows for autocatalytic subnetworks. And that's something which is really challenging, and we are trying to analyze. So thank you so much for your attention, and that's all from my side.